Hi everyone, welcome to the first lecture of Calculus 2. In Calculus 2, our main focus is on integration, integrals, and their applications. Now if we contrast to Calculus 1, Calculus 1 was all about derivatives. And in particular, derivatives came out of this tangent line problem, finding the equation of the tangent line to a curve at a point. There's a similar geometric motivating problem for integrals in integral calculus. And this is the area problem. How do we find the area of a region? In particular, an area of a region which has a curved boundary. So in this particular lecture, we're just going to focus on the area problem and see what we know about it and see what kinds of questions come up. So what is the meaning of the word area? Well, if we're going to talk about area, we should know what we mean by area. And, a quick look at Cambridge Dictionary comes up with, it's the particular part of a place, piece of land, or country. Well, okay, that doesn't help us very much because intuitively we're thinking of area as some sort of quantity that measures the size of an object. So let's look at the second definition. The size of a flat surface calculated by multiplying its length by its width. Oh, okay, so this is getting more to the point of what area is in terms of how we calculate it, but this is still not quite what we want because this is only talking about a rectangle. The area is the length times the width. Okay, so what about other regions? What are their areas? Well, part C, a subject or activity or part of it. Okay, that's not even close to what we want in terms of the term area. A quick peek at Wikipedia says the area is a physical quantity expressing the size or part of a surface. Oh, that's a little bit better. Okay, so that's a physical quantity which tells us something about size. That's kind of what we want. But this is lacking in the sense that it doesn't tell us how to compute. What is this physical quantity? How do we compute it? So let's look at some of our regions over here. Here I've got them drawn on a grid, and a square grid. And so I'm just going to identify, there's this one square we'll say has dimensions 1 by 1. So this is a unit square. It's got unit side lengths. Now what are these units? Well, they could be 1 centimeter, 1 meter, 1 kilometer. It all depends on the context in which you're working. So we're just going to call this 1 unit, and therefore this is a unit square, whatever the units are that you're working in. And so our idea of capturing what an area is should really be how many of these unit squares does it take to fill up the region. So for example, if I'm looking at a rectangle, what is the area of this rectangle? Well, it should be how many unit squares does it take to fill up the interior of that rectangle. And we see that the rectangle is 2 high, it's 3 wide, and it's got 6 squares inside it that fill it up, and we can get that value by multiplying the 2 by the 3. So this is exactly capturing this part of the definition of area. It's the area of a surface calculated by multiplying its length and its width. So that's for the rectangle. But what about things that aren't rectangular? What about, for example, this region here, this trapezoid? How do we find its area? Well, again, we're trying to figure out how many unit squares does it take to fill it up. So one thing we can note is that by cutting up a region and sort of rearranging the pieces, we don't change the area. So I can imagine cutting off this portion of the triangle and then just moving it to the other side. And if I do that, what I get is I get that filled in region, and so the region then just becomes what is equivalent to a 2 by 2 square. And so now I can refer to the area of a rectangle as its length times its width. So the area of this thing is 4. What about a triangle? What's the area of a triangle? Well, we can imagine that the triangle is sitting inside a larger rectangle. In this case, it just happens to be a square. And this is a 3 by 3 square, so the area of the square is length times width, or 9, and so the area of the triangle would be 1/2 of 9, or 9/2. Okay, so this, all very intuitive things we very well know, how to find areas of rectangles and areas of other shapes that have straight sides. But what about the area of a circle? What about the area of anything with a curved side, for that matter? It's seems rather difficult now to chop it up so that it has straight edges, so then we can refer back to the area of the rectangle as our building blocks for area. Well, what is the area of a circle? Well, this is one of those things that's been ingrained in our memories for quite a number of years through elementary and middle school and high school. The area would be pi r squared. But have you ever thought about where this comes from? Where does this formula a equals pi r squared comes from? It has to come from, there is some definition of what an area is, and in the case of the circle, this is the formula that you can use to compute the area. So how do you get that formula? This is the kind of question we're going to answer with integral calculus. How do we find the area of these regions that have curved sides? That's our motivating problem. How do we find these areas? In particular, how do we come up with this area of a circle formula, pi r squared? Okay. So we're just going to start by looking at a few basic examples in the context of areas under graphs of functions, and we'll build up some ideas as to how to approximate areas and then hopefully come up with a working definition of what an area is, built from the area of a rectangle, but then moving up to what is the definition of an area under of a region with sort of these curved sides, or a general region in general. So let's look at a couple of examples. Find the area of the region in the coordinate plane bounded by the coordinate axes and the lines x equals 2, y equals 3. So I've got the line x equals 2, the vertical line, and the horizontal line y equals 3 sketched. And we also want the region that's bound by the coordinate axes. So we're talking about this region here. And we want to know its area. So in some sense you can think of this as the area under the curve y equals 3 between x equals 0 and x equals 2. What is that area? Well, this is an area of a rectangle, or the region is a rectangle, so the area that we're looking for is the area of a rectangle, which is base times height. The base is 2 units wide, the height, that's 3 units, so the area, which is base times height, is 2 times 3, or 6. Okay, so we're working our way up to some more interesting examples. We're just starting with some of the basics. And the key here to notice is that whenever we're computing these areas, we're in some sense appealing to the area of a rectangle. At some point, we're going to have to generalize that to more complicated regions. So find the area of the region in the coordinate plane bounded by the x-axis and the lines y equals 2x and x equals 3. So the region sketched here, we're interested in this area. Now that's a this is a triangle. We can think of it as embedded inside this larger rectangle. And so because this is a triangle, we know that the area is 1/2 the base times the height, or in other words, 1/2 of the area of the encompassing rectangle. So this is 1/2 base times height, which is 1/2. What's the base? It looks like it's about a 3 here, and it is, x equals 3. And the height is 6, so it's 1/2, 3 times 6, or 9. So the area of that region is 9. What about this next region? Find the area of the region in the coordinate plane bounded by the x-axis and the lines y equals x squared and x equals 3. So now we're trapped below y equals x squared, and this line x equals 3. What's the area of that region? Well, you start to see that we're already in trouble. This is a curved side. No longer can we cut this thing up or rearrange it or look at it as embedded inside some larger object that have straight sides, because I can't figure out how to deal with this curved side as of yet. So I can't use the area of a rectangle to get this area just yet. I might have to do something with that. So here, we're running into a slight problem. What is the area of this region? Well, this is the motivating problem of integral calculus, of this entire course. This is our motivating problem. How do we calculate the area of a region where we've got curved sides? Now, some of you may have seen calculus before, and you're probably thinking to yourself, why don't you just take the antiderivative and all that kind of stuff? Well, the point is we don't know anything about that yet, right? We're starting with the very fundamentals right here. What is area? I have to make the connection of area with the area of a rectangle, use that to sort of generalize what this notion of area is, and then see how antiderivatives, which we'll soon see, are even connected to this problem. So that's in the future. Right now we're still building up this idea. What is area? How can we even compute it? So let's go ahead and continue with this problem of finding the area of this curved region. So in this example we're going to look at estimating the area of the region under the curve to the left of x equals 3 and above the axes. Now the rules of the game are for doing these area estimations is we only know one thing, the area of a rectangle. That's it. We're playing naive here, but that's the only thing we know. And we're going to try to come up with a way to define what area is for more complicated regions and also come up with a technique for calculating the area. And again, let me reiterate, we're only using the area of the rectangle as our starting point. So what can we do to estimate the area of this rectangle? Well, we could cap it off at the height there, so that's 0.3, 9, so a rectangle of height 9. Notice the scale on the axes is different from the x and y axes, and that's why this looks like it's shorter than it is wide, but it's actually taller than it is wide, if you look at the values of the y value versus the x value. So we could cap it off and compute the area of this big rectangle. That would be 3 times 9, so 27. Well, the problem is that that's a terrible estimate, because you can see that our error in our estimate is all this region, and that looks to be even bigger than the actual area we're trying to compute. So using one rectangle in this case isn't so good. So what we're going to do is we're going to use more than one rectangle. Now what I've done is I'm going to do a sort of a condensed version of this estimation here in this video. If you haven't seen this stuff before, or you want to have a little bit more slow and detailed approach to this, I have recorded an extended video where I go through a couple concrete calculations related to this before I get to the more general case. In this particular video right now, I'm going to do one concrete calculation and then go into the general case. So if you find that this might be going a little bit too fast for you, there is an extended version of this particular example, which I've linked to below. Okay, so what can we do? Well, I want to use rectangles to estimate this area. So what I'm going to do is I'm going to slice up the region and then approximate each slice. So here I'm going to slice it up into 3 regions. And why 3? Well, because then each slice lands on a nice integer value. And it makes the calculations a little bit nicer for the example, for illustrative purposes. But in general, you don't make such choices due to making these numbers nice. You make them so that you get good estimates. And we'll see how we can modify these choices in a second to get better estimates. So what I'm going to do is I'm going to split the interval 0 to 3 into subintervals, 3 of them, 3 subintervals. What are my subintervals? 0 to 1, 1 to 2, and 2 to 3. Now I'm left with the challenge of estimating the subintervals. What I'm going to do to estimate those is I'm going to do what I did as an initial first rather terrible estimate for the whole region, is I'm just going to cap each of these subintervals by some height, some straight height, and then use that resulting rectangle to estimate it. Now I have some choice as to how I want to make the height. I could make it really high, but of course that would be rather silly because then I get all this extra stuff that I'm counting in the area of my estimate, which is my error. I could make it low, but I don't want to make it too low because then I'm again making it a rather poor estimate. So I want to try to cap it off somewhere between the maximum and minimum values of the function on the interval. Now, rather than thinking too hard about where the max and min occurs, in this example it's not so difficult because it's strictly increasing, but if you had an oscillating function, you'd have a little bit more thought involved into figuring out where to cap it off. A more classical way to do this is to just look at the right and the left hand endpoints and use either one of those as a place to cap it off. So what we're going to do is we're going to focus on just the right-hand endpoint right now. So I'm going to look at the right-hand endpoint, and I'm going to use that as a place to cap it off. There's my rectangle that I'm going to use to estimate the area under the curve. Again, let me reiterate that we've got some flexibility as to how we can choose to cap this off. I'm just going to choose the right-hand endpoint and draw a horizontal line through it and use that as the top of my rectangle. And I'll do that all the way across. So I'm using these right-hand endpoints all the way along. So what we're going to do is now just work out the values of these areas of these rectangles. So these are our right-hand endpoints. And what do we get? We get that the actual area, the area of the blue region, is approximately the area of these rectangles. Let's extend them down here so you see that it's these whole rectangles is what we're using. What are the areas of these three rectangles? Well, each one of them has a base of 1. I've split it up. I've split that interval of length 3 up into 3 subintervals, and I probably should have said of equal width, just to be clear. That's why I can assume that they're all of width 1, because I've taken an interval of length 3 and split it up into 3 equal width intervals. Now each one of them has a base of 1. What's the height of the first rectangle? Well, it'll be the right-hand endpoint, which is x value 1. Plug it into the function, that's 1 squared. So that's the height of the first rectangle. Base of the second times the height of the second, plus base of the third times height of the third. We get our value of 14. So that's the area of those three rectangles added up. So I know my actual area is smaller than 14. But I had some flexibility in how I choose to cap off these rectangles. So another choice I could have used is our left-hand endpoints. What are our left-hand endpoints going to do? Well, on each interval I choose the left-hand endpoint, go to the function value, draw a horizontal line to cap off that rectangle. First one is height 0, so it doesn't really give me any rectangle of any area, and then all the way across. So I get these rectangles now. And we can see, since the function's increasing, that all of these rectangles are sitting below the actual area I'm interested in. So some of these areas are lower bounds to the actual area under the curve. Width of the first rectangle is 1. The height is 0. Width of the second rectangle is 1. Height is 1 squared. Width of the third is 1. Height is 2 squared. And so we've got a value of 5. And so what we have found then is that the actual area is smaller than 14, bigger than 5. So there is our estimate. Area sits between 5 and 14. You might think to yourself, that's a pretty poor estimate. It's between 5 and 14. There's a lot of room between 5 and 14. So we haven't done very well at all. And, of course, you're right. We haven't done very well at all. But the point is that this technique that we're using can extend so that we can refine our estimates to become better and better and better. So here's our question. Can we do better? And if so, how? So let's have a look at this. So here's our curve, and I've just sketched in the right-hand, 3 rectangles using the right-hand endpoints to cap it off. The sum of the areas of these rectangles is written up here. It's 14. It's what we call the Riemann sum, after German mathematician Bernhard Riemann, who worked on this problem in the mid-1800s. In particular, we would call this the right-hand Riemann sum, because we're using right-hand endpoints to cap off those rectangles. So we got our value of 14. Here's the thing. If we use more rectangles, we should get a better estimate. Now, the thing to keep in mind is that the reason this estimate was rather poor was because we have all these rectangles overhanging the region. So this is all extra stuff. All this blue stuff is extra stuff that we don't want to count, because that's our error in our estimate of using these rectangles to approximate this actual area, which is this sort of shaded region here. That's the actual area. All of this stuff is overhang. So how can we make it better? Well, if I increase the number of rectangles, you can see that the stuff that's overhanging is shrinking. So if I use 15 rectangles, I get a Riemann sum of 9.92. Already we've gone from 14 as an estimate to 9.92. So if I keep going, maybe up to 30 rectangles, I've got an
estimate of 9.45. We're getting pretty good estimates here. The more rectangles we use, the better they are at fitting in that region that we're trying to estimate. There's still a little bit of overhang, and that's our error, but they're doing a much better job of approximating that region. And I can crank this up all the way up to, and I'll go up to 80. So there's 80 rectangles, and we get our sum of 9.17. So that's an upper bound. Our actual area is smaller than 9.17. Now, the thing to keep in mind here is that all that's happening is we're just adding up the area of all these rectangles. So I just need to know the base of all these rectangles and their corresponding heights. How do I get the base of all these rectangles? Well, I've taken an interval of length 3 and split it up into 80 subintervals. So the length of each subinterval is 3 divided by 80. So that's all easy to work out. What about the heights? Well, now I'm just taking the endpoint of each subinterval, which, as we'll see, is quite straightforward to work out, plugging it into the function and adding them all up. So all we're doing is arithmetic to get these values. Nothing complicated here. We're just doing arithmetic. We're just adding up 80 products. 80 products and then adding them all up. So something that a computer can do very easily. It's straightforward to program into a computer. So the actual computation is not difficult. What we're generating is the ideas behind this right now. Okay, so we've done our right-hand Riemann sums, but we also saw that we could do with the left-hand sides as well. So we'll start with the left-hand sides. So I'm going to drag this. In fact, we could use any height between the right and the left. For example, we could use a midpoint, and then we get another Riemann sum, and we can work out these values. I just need to know the midpoints of each of the intervals. Perfectly acceptable ways to approach this problem as well. I'm going to look at the other one we did, which was a left-hand sum. So our left-hand Riemann sum, the sum of all of these areas of these rectangles, was 5. Now what happens if we crank that number up? More rectangles we use, the blank space, the white space underneath the curve and above the rectangle is stuff that's actually in the region we're trying to compute the area of, but we're missing it with this approximation. So we'd like that area of those white regions to shrink away to get a better approximation, a better estimate. And we can see that the more rectangles we use, the better job they do at fitting into those spaces. So if again I use 80 rectangles, I now have a lower bound on my actual area as 8.83. So I had an upper bound of 9.17, a lower bound of 8.83. I know my actual areas between those two numbers. That's a pretty good approximation as compared to what we started with, was the 5 and 14 approximations or estimates. And this is how we can continue on estimating these things. Now ideally, we'd like to have the exact value of the area, not an estimate. Our goal was to try to find the exact value. Can you think about how we would do this? We want the exact value. And we've just seen that the more rectangles you take, the better the approximation becomes. Now, have we done anything that allows us to look at what happens as n gets bigger and bigger and bigger and bigger and bigger without bound, and look at what happens in the process? That's a limit. That's a limit. We would really like to find the area of this region in terms of n, the number of rectangles we're using, and then watch what happens as n goes to infinity. What happens as n goes to infinity? Does the limit approach something? And if it does, should that be what we call the area under the curve? This is where we're going with these ideas. We're using rectangles to estimate the areas. Then we're going to try to take the limit as the number of rectangles goes to infinity and get an exact value for the area, an exact value. So can we do better? And the answer is a resounding yes, we can. We use more rectangles. So let's look at the details. Use more rectangles. We'll start with the curve again. On the interval from 0 to 3. How do we use more rectangles? Well, we split the interval into n subintervals. And here we're going to keep them of equal width, which we'll call delta x. So what do they look like? Well, it'll be x sub 0 to x sub 1 This is what we typically call these intermediate points once we do the split. X sub 1 to x sub 2, x sub 2 to x sub 3, and so on, all the way down to x sub n minus 1 to x sub n. So here's what they look like in the diagram. That's x sub 0, which is the same as 0. And then we've got an x sub 1, an x sub 2, an x sub 3, and all the way along. Typical point somewhere in the middle looks like an x sub I minus 1 to an x sub I, and we keep going. And the second last point would be an x sub n minus 1, and then the last point is x sub n. And so there's our slices. We'd now like to estimate the areas of each of these slices all the way along. What are the areas of each of these slices? How do we estimate those? We could use the right-hand endpoints. If we use the right-hand endpoints, we get that the area is approximately the right-hand sum using n subintervals. And what does that look like? Well, the width of a subinterval we've called delta x. So one of these, maybe I'll do it over here. One of these subintervals, there's our general one there. The width is delta x. What is delta x? Delta x is we've taken an interval of length 3 and we've divided it into n subintervals. Length 3 because, well, it's the right-hand endpoint minus the left-hand endpoint divided by n. So 3 over n is the delta x. And so what is our right-hand sum looking like? Well, it's just the area of all these rectangles as we go along where we're using the right-hand sum at every point. So it's going to be the base times the height of the first right-hand endpoint. That's x sub 1 all squared, plus the base times the height of the second endpoint, x sub 2 all squared, plus, and we keep going, plus the last interval, the base, delta x, times the height of the last one all squared. That's x sub n squared. So there is our value of our right-hand sum. Now we would like to have this expression just in terms of the length of the interval and the number of rectangles we're using. So we need to know these values of these x sub i's. So let's have a look at that. From this diagram we see that x sub 0 is 0. What's x sub 1? Well, x sub 1 is obtained by just moving over delta x units from the place you're starting at. So it's 0 plus delta x, or in other words, it's delta x. What's x sub 2? Well, I had to move 2 delta x units over from 0. So that's just 2 delta x. What about x sub 3? Well, that would be 3 delta x. And so on, all the way down to x sub n. That would have been just starting at 0, I have to move over delta x units n times. So that's n times delta x. But remember, delta x was 3 over n, so this is just 3. And that's a good way to check to see if you've made any mistakes here, because it better be, x sub n better be 3, because that's the last endpoint of the whole interval. Okay, so those are our values for our x sub i's. So what that means is we've got a delta x, x sub 1 all squared. X sub 1 is just delta x, so that's delta x squared, plus delta x times 2 delta x squared, plus dot dot dot, plus delta x times n delta x all squared. And notice that every term in this sum has a delta x and another one squared. So there's a delta x cubed in every term. If I pull them all out, pull all those delta x cubes all out, then what I'm left with is a 1 squared in the first one, plus a 2 squared from the second one, plus a 3 squared, plus dot dot dot, all the way up to n squared. And there is our formula for our right-hand Riemann sum using n rectangles. Check it for the value when n was 3, and you'll see that you get what we had above. You get that value of 14. And all the values we had in that applet as I was dragging the slide around were just computed by using this formula here. Plug the various values of n in. So the larger the n is, the better this number approximates the actual area under the curve. We could do the same thing for the left endpoints. For the left endpoints. What would the left endpoints look like? Well, on each curve, they're going to be these, or in each interval, there are these smaller ones. Function's increasing, so these left-hand endpoints below the curve. So that's our L sub n. And you can do the exact same calculation that we did above, and you'll find that you get still a delta x cubed. And then what is our sum going to be? Well, in this case, rather than going and using the x sub 1 value up to the x sub n value, as we did in the right-hand sum, we're using the left-hand endpoints on each interval. So for the left-hand endpoints of each interval, we're starting with x sub 0 and running all the way up to x sub n minus 1. And so those were going to give us the values of 0 squared plus 1 squared plus dot 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 plus n minus 1 squared. You can check that yourself doing the same calculation above. This is just what the result's going to give you. And so there we go. So that's basically our process for estimating the area under a curve. Slice it up into a bunch of intervals. On each slice, use a rectangle to approximate the area under the curve. How you choose your rectangle really depends on how high you take it. Do you use the right hand or left hand endpoints or some other point in the middle of the interval to construct the height? And then once you've got all those rectangles, you add them up, and that's the process for coming up with the estimate for the area under the curve. We've got these two estimates now. We have that the actual area is always smaller than Rn, but always bigger than Ln. We've got expressions for Rn and Ln. Let's see what happens in their limit. The limit as n goes to infinity of Rn is the limit as n goes to infinity of, and now it was delta x cubed, so that was 3 over n, all cubed, times 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. Okay, so we're in a bit of a bind here. I want to compute the limit as n goes to infinity of this expression. The problem is I don't know how to deal with this dot dot dot. If we think back to Calculus 1 and all the limit expressions we've computed, I'd really like this to be some sort of closed form, and some function without this dot 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 in it. And it turns out we can. We can write it in that way. There is a nice identity that allows us to rewrite the sum of these consecutive squares as a rational function of n. We're going to talk about this identity more next lecture, but I'm going to use it here just so you can see how these identities that we're going to develop get used in practice. So it turns out that the sum of these consecutive squares is equal to n times n plus 1 times 2n plus 1 all over 6. So that is just an identity. That's an identity. Why is that useful here? Well, now if we look at this this right-hand side, you see that that's just a rational function. These are things we worked on in Calculus 1, computing limits of rational functions. So we know how to compute this limit. I'm just going to simplify it a little bit more just so we can see. So this is 3 cubed divided by 6. So I can cancel one of the 3's and the 6 with one of the 3's up there. So that gives me a 9 halves. There's an n cubed in the denominator. So I'm going to write that here, n cubed. And what's the numerator? It's n times n plus 1 times 2n plus 1. How do we compute this limit? Well, it's a rational function. Taking the limit as n goes to infinity, all I care about are the leading coefficients. If they're of the same degree, if the numerator and denominator have the same degree, they do. They're both degree 3 polynomials. So all that matters is the leading coefficient. The leading coefficient on the top is a 9. Oh, but wait, there's another factor over here. So it's a 9 times 2 is the leading coefficient of the top. If we expanded it all out, that's the leading coefficient of the n cubed term. It's a 2n cubed times 9, or an 18n cubed is the highest term there. And on the bottom, it's just the 2. Oh, but these 2's could cancel off. And when I do, I shouldn't actually write that they cancel off in this way. I'm going to cancel them in the next step. So maybe I should be a little bit more careful here. The value of this limit is the ratio of their leading coefficients, which is 9 times 2 over 2. Now I can cancel the 2's and get a value of 9 for the limit. So we do the exact same thing for the left hand
sums. So we're looking at the limit as n goes to infinity of 3 over n cubed, 0 squared plus 1 squared plus, now I don't have to write the 0 squared, I'm just writing it so we see that there's a pattern here that was being followed. So now I need to come up with a closed form for what's happening here on the sum of consecutive squares. The closed form was if you go from 1 all the way up to n, all squared, then it's that last term times the last term plus 1 times 2 times the last term plus n, or the n value of the last term. And so in this case, our last term is n minus 1. So it will be up to n minus 1, n minus 1 plus 1, so that's just n, times 2n minus 1 plus 1. So 2 times n minus 1 is 2n minus 2 plus a 1, so that's a 2n minus 1. And that's all over 6. So again, we're just using this identity, but realizing that it's not n that we're stopping at, or n squared. It's n minus 1 squared. So I'm just using n minus 1 everywhere I see an n in the identity above. Now what do we have? Well, it's a degree 3 over a degree 3. Same process as above. The limit of that rational function is the ratio of its leading coefficients. So the leading coefficients would be the 3 cubed times 2. The leading coefficient on the bottom is the 6. And so that leaves us with also a value of 9. Now here is the cool part. So therefore, we have that the area, which is always trapped between ln and rn for all n. What does that mean? Well, it means that the limit as n goes to infinity of ln has to be below the value of a. A is constant, so I could really stick a limit in front of it, but it's not going to change anything because it's just a constant number, is also less than the value of this limit. These are both going to 9, and so therefore this implies that the value of a is 9. Why is that the case? This is the squeeze theorem. We have that this number is trapped between these two functions, functions of n, these two functions of n, for all n. So it's got to be trapped between their limits, and the limits go to the same place, so a has to be equal to 9. So this was by the squeeze theorem. And we've got our value of our area under the curve exactly. So if we back up just a little bit, when we said find the area of the region, and I had a equals question mark, this is a motivating problem of integral calculus, we've solved this problem now. What's the area of the region? The area of the region is 9. We found it. We found it using calculus. We used limits. We did some process of approximating and then refining our approximation and then working out a value of a limit, and we got the value exactly. This should sort of be reminiscent of what we did in Calculus 1. We wanted to find the slope of the tangent line. Well, we took secant lines, lines through 2 points on the curve, and then we refined by taking the secondary point closer and closer to the first point through this process of the limit as their distance, their x distance, or their limit as h goes to 0. And then we ended up with the slope of the tangent line by using this limiting process of slopes of secant lines. Here, we found the area through a limiting process of using areas of rectangles. This is the motivating problem of calculus. Now, much like in Calculus 1, where after using the limit definition to compute derivatives, we did find that there was a quicker way to do this. This gave rise to the differentiation rules. We had like the product rule, quotient rule, chain rule, power rule, all of these quick methods for computing derivatives. We're going to see that the same is true here. We're going to be able to compute areas under curves, particular functions, without having to go through that long process of computing Riemann sums and the ultimate limit. But we've got to take baby steps to get to that stage. We're still developing the idea of what an area is. We've got to make the connection with derivatives or antiderivatives before we can get to what's known as the fundamental theorem of calculus, which makes this connection between areas and antiderivatives. So we're almost there, but we're still progressing through what is the area and ultimately what is an integral before we look at quick techniques for calculating them. So that's it for this particular series of examples. What we're going to do in the next video, though, is continue on with these notes and look at the general process, summarizing what we've done, looking at the general process, and then looking at another example of doing this exact process for computing the area under a curve. And then we'll make a connection with areas under curves and velocity and distances in physics. And then that'll mark the end of this introduction, this motivating lecture into integral calculus.